Hello and welcome. This is going to be lecture number 11. Put the lecture number and the date at the top of your notes, and we'll go ahead and get started. We're going to be looking at a historical perspective of motion and talking about a few important scientists. All right, the first of four scientists I want you to know is Aristotle. And Aristotle was observing motion, and he noticed that some objects seem to move on their own, specifically objects when they're dropped. Like if I take a stone and I just release it, it's going to drop straight down. Or smoke from a fire goes straight up. So here we have some smoke going straight up. So what's interesting about this motion is that it doesn't seem to have any sort of source. We later realized that both of these, the source of the motion here is the force of gravity, either pulling the rock down or causing air to rush in underneath the smoke, pushing it up. But since they didn't really understand gravity super well, they just called this type of motion natural motion. This was just natural motion. And so it was things that were falling or going straight up. And so they just assumed there was something inherent to the earth that caused things to move either straight up or straight down, and that was just natural motion. As a side note, they thought that things out in the solar system, their natural state was to move in circles. So they would observe the planets and the stars all moving in circles. Circular motion out in the sky was considered natural. But there's other motion possible, and that is motion side to side. They had a different way of describing this. So if anything ever moved side to side, they called this imposed motion. So side to side was imposed motion. So natural motion was straight up and down. Side to side motion was imposed. And a lot of translations call it violent motion, which is kind of an interesting translation. But you have, natural and violent motion. So natural motion was up / down, and violent motion was side to side. Now, obviously, this isn't the whole picture. They were neglecting the force of gravity here and did not understand how objects were moving in outer space very well. But the important thing was that they started thinking about these things and trying to understand natural phenomena that was happening around them all the time, but trying to actually describe it and explain why certain things happen. We all see that things that when they're dropped, they fall. At least Aristotle was one of the first that started to try to get to the bottom of why that is. Much after Aristotle came along a scientist named Copernicus. We're talking 1400s to 1500s. And Copernicus was the first person, well, we'll at least say he was the first person, there could have been some before him, who proposed the idea that the Earth is in motion. This is a very revolutionary idea because just sitting here on the Earth feels very much like it's not moving at all, that it's just completely stationary. We would think that if it was moving, we would be able to feel it somehow. But Copernicus was the first to really think that, well, possibly it's moving, but because we're all moving along with it, we just can't really sense that. And this helped really to explain the strange movement of the planets relative to the stars. So all of the stars move together. They all circle the North Star, the only star that doesn't move in the sky, at least in the northern hemisphere. But the planets move very differently from that. And a lot of different ideas have been suggested that maybe the sun orbits the Earth, but the other planets move in circles outside of the Earth. But Copernicus said all this motion that makes a lot more sense if you put the sun in the center, and then you have all of the planets, including Earth, go around. And this model of the solar system does make a whole lot more sense. The sun is much more massive than the Earth, so really the Earth orbits the sun, although you could even say they both orbit a common point, but that common point is actually within the sun because the sun is so massive. And so this was Copernicus's big contribution to motion was the Earth orbiting the sun. All right, the third scientist I would like you to know is Galileo. Galileo definitely built upon Copernicus's ideas. He was a big supporter of the heliocentric view, that means sun in the center view that Copernicus came up with. And another really big contribution Galileo made to motion was that he said no force is needed to keep an object in motion, which sounds kind of bizarre even saying it today, that no force is needed to keep an object in motion. But he did a lot of thought experiments about a ball rolling down a ramp. And when a ball rolls down a ramp, it returns to the same height that it started at the other side, minus a little bit for friction. But Galileo's idea is that if there was no friction, an object in motion would stay in motion forever. So if we perform this thought experiment of a ball rolling down a ramp, but we never let that ball go up the ramp on the other side, it should just move forever to infinity. So this was one way he thought about it. Another was just the idea that a ball going down a ramp increases speed, but a ball going up a ramp decreases speed. So a ball on a flat plane should just travel at a constant speed. And this really laid a lot of groundwork for our next scientist to come along with his three laws. So the fourth scientist I want you to know is Isaac Newton. Very important scientist for so many reasons, but what we're going to focus in on are the three laws of motion. So he really built on what Galileo was laying out, especially in his first law, which is just that an object in motion stays in motion at a constant speed unless acted upon by an unbalanced force. So he took a lot of what Galileo was doing and just put it into these formal laws. Now, his second law deals with this idea of acceleration. So forces don't cause motion, forces cause acceleration, which is different than motion. Acceleration is just a change in velocity. We can change velocity in a lot of different ways. When an object orbits another object, its velocity is changing because its direction is always changing. That's caused by the force of gravity, but the speed never changes. So here, let's make it very clear that acceleration is different from speed / velocity. So the force doesn't cause a certain speed or velocity. It causes an object to just change its velocity. And so this is a really important idea, and this was his second law. And then his third law is all about equal and opposite reactions. So I think what our big takeaway here from Newton is he codified the understanding of motion into three laws and then really built upon it. And then this forces cause acceleration part is really important for his second law and how we now think about forces. Okay, so I'll embed a few more questions here to help you memorize these four scientists that I really want you to know. And that's that for this lecture video. Have a good rest of your day.